Our first presentation will be an overview and on this heat storage approach and an assessment, a quick review of our status by our coordinator, Dr. Abhishek Singh.
Yes. Thanks, Nicholas. And thank you everyone for joining this webinar. So in this very short presentation, I will talk about the approach that we have taken in this project and its current status. So this project started almost 2 years ago, little more than 2 years ago, 2023 June, and it's a 4-year project. So we still have little less than 2 years from now to achieve our goals. This consortium consists of 10 entities, universities, national labs, and also partners from commercial side. We have end users as well as technology developer who are part of this consortium. So the question is, what are we trying to achieve here? In this project, our focus is on industrial decarbonization. So in this graph, you can see we have different sectors. Industrial sectors, they have different requirement from temperature point of view as well as the energy demand they have. And it also, you can see differences between requirement for electricity and also the heat. And typically, heat is actually more prominent requirement from the industry. And the question is how to decarbonize that. There are so many different solutions, definitely, but one prominent way is to use renewable electricity for industrial electrification. So you can generate heat that you use and decarbonize the industry. But you want to use electricity generated using renewable sources. You can see here we have a extremely good potential for industrial electrification that could reduce the carbon emission up to 670 megaton, which is much more than what is the current target. But then there are challenges, of course. That's what we are trying to solve or reach out to in this particular project. Now, when we try to integrate renewable electricity with any demand, then we have to all take care of supply and demand mismatch. And for that purpose, storage is a useful solution, and that's what we are trying to develop here in this project. Yeah. So we choose to use this renewable electrification of our storage. I will explain you more about what exactly type of storage we are using, because we can achieve high temperatures. So you can also serve a variety of industries using this solution. And our focus is only on heat generation from this storage solution, which is the majority of requirement. And the proposed solution is suitable for several different types of industries, especially the ones like steel, cement, and chemical industry, which is hard to decarbonize. And we also plan to use the waste heat from industry that is available. And we are also trying to explore how we can have a synergy between industrial heating, so the heat that we need to provide, or the heat which is the waste heat which is available, and also the district heating system. So that is part of our investigation in this project. Now, if we think about what has been current practice right now in industry, they use sensible heat storage systems. In the steel industry, they have these copper stoves. So basically, they have this fire brick pattern that they use to store heat from combustion flue gases. So it's like when they are producing these flue gases, they store that heat into these bricks, and then they pass cold air, which heats up, and they use it in their system. Similar type of concepts are also being utilized in CSP power generation plants, mostly the air operated ones. Now, this is mostly based on sensible storage solution, which is effective, but challenge with the sensible solution is that I'm just missing one slide here. So far they were using whatever is the waste or the burning of fossil fuel. But now the idea is, what if we use cheap, excessive electricity generated using renewable sources like solar and wind? And within this understanding, there were several projects that has been started in last few years. And you can see here some of those examples in which researchers try to use renewable electricity to store heat in sensible storage solutions. Here we are trying to go one step further because sensible storage is, let's say, low in energy density. So we are trying to use redox oxide made bricks. So it's more like a honeycomb structures that could basically increase the energy density of the because in this material we will store not only the sensible heat but also a chemical heat, but which you can see here the redox reaction. The first step is when you have metal oxide, you provide heat to it, you reduce the metal oxide, produces oxygen in this process. When you reverse the process, you can basically retrieve the heat you stored in the chemical form, and then you can do the same, and you can also retrieve the sensible energy storage, sensible energy that is stored in during the charging process. So it depends upon the delta T you are looking for. So that is, let's say, the backbone of our project. And here is a conceptual diagram. So idea is rather straightforward, that you have electricity, which is cheap access because you are generating that from the renewable sources. You store that heat, electricity in the form of heat by having the charging of these redox material. And in the reverse process, when the electricity is not available but you have the heating demand, you reverse the process, you reverse the chemical reaction, and then you produce hot air, which is very useful for several industries. In this case, we have partners from a steel industry and also recycling industry where this fits pretty well, and there are other possibilities in terms of application too. Now this is the current status. So we are investigating this particular storage solution from 3 different scales: material, reactor, and system. So what you see here is the current status. So we have done, I think, remarkable progress from the material development side. You can see we have material CS10MO. You will hear more about this in the next presentation. It has shown good cyclability, and also we achieved our storage density target by a large margin. So our target was 300 kilowatt hour per meter cube, but our material shows around 800, actually more than 800 kilowatt hour per meter cube energy density. And now our colleagues are in process of making scaled up structured material. From the reactor side, we decided to have a pre-prototype reactor. So it's the single heating element surrounded by the reactive material to learn how the reactor will behave, and so that we can achieve a final goal of having much larger storage system. We also develop a numerical model to support this development, and we have colleagues who are looking for the testing of some novel insulation configurations and characterizing them, so we have better idea what we would like to use for our pilot scale testing. From the system scale development, we have models that has a dynamic integration of the storage system with the application, Tata Steel and Alucha cases. So basically steel making, the blast furnace process, and also the recycling process. And we have some first results from one of the process. So we will also show that development today. We also have a very a good team for doing LC and economic analysis. So we also have some of those results already out from these development. So I stop here from my side. I hope I did not take too much time. And then I will let my colleagues to go and provide more details about all these 3 scales that we are working on.
Thank you, Abhishek. So the next phase of our workshop is presentation by our colleague Christos Agrafiotis from DLR on looking in more detail at the actual storage material and its development. Okay.
So now here, thanks for the introduction. I will present a work, let's say, on how we screen and develop the materials that we use for this application. Essentially, it covers work of 3 partners in this project, ourselves, CERTH, and LANDSON, a Danish partner that is active on extrusion. Next click, please. Okay. First of all, the idea, as Abhishek said, is that we have to build a unit will be made out of porous built-in blocks, and by this we mean honeycombs, foams, or granules. And the idea, if you click once more, you will see that this approach induces flexibility. We can make such a unit, let's say, from different materials, fine-tune porosity, distribute these materials along the bed, for instance. And the whole idea is to use different porous structures, as you see there, cylinders, forms, or even 3D printed structures that you see the white objects at the bottom. And the idea is to maximize, let's say, the volumetric efficiency and fill, let's say, all this volume, the maximum volume of the thermochemical reactor heat exchanger with materials that can be exploited. And by this, if we click once or twice more, we will see that we can also add to these redox materials sensible only materials, chemically inert materials like bricks, cordierite, or metal slag, that they can be used for sensible heat storage, like they were the bricks we saw in the first slides, in regions where, for instance, the temperature is not high enough to induce the reduction oxidation reactions, or our materials, these redox materials, are too sensitive and suffer sintering and deactivation. One more word on why we select to use foams, simply because the foams, in contrast to the honeycombs that are, let's say, unidirectional, they allow for radial mixing. With this tortuous path that they have, the gas that goes in can flow not only, let's say, along the main axis as you see it there, but also sideways along the radius of the cylinder, for instance, in the schematic. So this enhances heat transfer, evens out, let's say, the flow distribution, and in general provides for better heat transfer from the solid, from the gas to the solid during charging, and to the reverse during discharging. And that's the rationale why we use such reticulated porous ceramic or ceramic foams. If we click on the next slide, we will see, for instance, okay, we want to make these porous honeycombs. Out of which materials? There are several kinds of oxides that they operate via this cyclic redox scheme that Abhishek showed before. One family is the cobalt oxide. You see with green the advantages and with red the disadvantages. Cobalt oxide has been used a lot as a model material because it's very reliable, cyclable. It has a very high reaction enthalpy and can operate for many, many cycles constantly. But on the other hand, it has high cost and potentially is considered toxic. Oxides based on, let's say, more abundant and cheaper elements like manganese iron mixed oxides, they also are cyclable, they are of lower cost, they are non-toxic, of course, but the problem is that the reaction enthalpy is not as high as that of cobalt oxide, for instance. Other combinations, including magnesium and manganese oxides, they perform well on reaction enthalpy and on cyclability. However, they need a very high temperature in order to initiate the reduction and therefore the reverse oxidation reaction, which can cause structural stability issues when these materials are cycled many, many times. Perovskites, on the other hand, they are cheap if based on abundant materials, non-toxic, they operate at lower temperature range, they exhibit good cyclability. However, these bird temperature range may cause issues as well, and of course the reaction enthalpy is not as high as cobalt oxides, for instance. However, based on these advantages, if we click, we will see that in our project here, we will focus on perovskites. For those who are not familiar, perovskites are mixed oxides of the formula AbO3, so it involves two cations and oxygen. And if we click, we will see how this will operate. The problem is that they operate as a partial reduction scheme. As you can see here, when they are heated, for instance, they don't go all the way to the reduced state of the oxide, but they lose some less amount of oxygen, which is denoted by the Greek delta and means the reduction extent. So they don't suffer any phase transformation. Essentially, they transform to an oxygen lean, let's say, solid oxide. And as a consequence, for instance, if we click, we will see that the heat effects of these reactions are less than cobalt oxide, which operates via a full structural transformation scheme, as you see in this reaction where cobalt 304 goes all the way to cobalt suboxide, and the amount of heat is higher. So in general, exactly because the perovskites operate with partial reduction, or otherwise called oxygen vacancies mechanisms, that's what explains the lower reaction enthalpy effects that we see on top. Okay, so we chose perovskites then. How we select these A-B cations, we can see here, for instance, different cations that are bivalent and trivalent that are used in the first two, in these cation sites, magnesium, calcium, strontium, barium, lanthanum, and so on. Or the second cation is transition metals like iron, manganese, and so on, which are, if you can see, most of them have a double valence, and that's basically where the redox functionality is happening. Okay. And of course, not all oxides are compatible with all others. They have to have compatible radii, these cations that you can see there in this Goldsmith's factor, which is a measure of the stability of this perovskite phase. Some criteria of choice, of course, as we said, we would like such oxides to have a high redox extent, which will induce a high delta H. For this, we can spare the experiments and have a first initial screening via computational techniques, as we will show later. If we screen down, let's say, the possible combination of cations, then we can apply additional criteria like low cost, high abundance, and low toxicity. And for this, a useful tool is what we will see by clicking next, is the so-called Herfindahl-Hirschman indexes, which shows the elements of the periodic table with different, let's say, coloration depending on their production, reserve, and abundance. And the moral of this table is that in general, if one wants to go for large-scale, high-volume production for any kind of application, one needs blue materials. With blue are, let's say, the most abundant, the ones with the highest reserve, the ones that are non-toxic, and so on. So in general, one should, let's say, look more towards the blue side of this periodic table rather than the red and yellow ones. And of course, if we click, we will see that this kind of materials are, for our case, calcium, magnesium, and strontium for the A site, and as I said before, transition metal cations like manganese, iron, aluminum, and titanium are the most common ones used for the B side. Fine, so that we have selected the, let's say, stock of our cations, and my colleague Daniel here will explain you very shortly, who is the expert on that, how we proceed in this computational screening before we delve into experiments.
So just in brief, we performed quantum mechanical calculations so without the need for any experimental inputs. We took a base composition which we knew works well, which is calcium manganese oxide. And we have replaced some of the elements in calcium manganese oxide by other elements, and we have calculated the performance or the capability of thermochemical heat storage in these doped compounds. So we checked if they are charge neutral, if they are expected to be stable, and then we calculated the redox thermochemistry of these materials, and for several thousands of compounds, and we could identify the ones which, from a theoretical perspective, are expected to be the most promising materials for such heat storage applications. Thank you.
And this, as we see, progressively reduces the number of, let's say, screen compositions from a very big one of 700 to begin with, somewhere down to some more feasible numbers. And this, let's say, other compositions can be grouped into families and can be synthesized, let's say, just typical representatives of the cations that are the most, let's say, possible to operate. And this is the approach that we followed. And if we go now to the next slide, we see, for instance, that some typical compositions that we tested in the right-hand side, and we see some of them are okay, some are melting, some occur dissociation, and some suffer dissociation and produce different phases on the perovskite. Some of them, those have good purity, they are stable up to high temperatures, and so on. We proceed with the families of, let's say, cation dopants and basic elements that more or less do not present any such problems of phase stability or melting or dissociation. Fine, then we go, okay, now we selected also, let's say, a narrower family of cations, and if we click now into the next slide, we have the issue of how we're going to build, let's say, and make these porous ceramics that we saw before. For instance, let's say that we start with a mixture that contains calcium, strontium, and manganese. We start from the precursors. These are powders. In our case, we use carbonates and oxides. So first we mix the powder mixing, because we have first to synthesize the perovskite phase, as we saw before, calcium manganite. Then if we click after the mixing, we have to sinter. As I said, the target is to have a homogeneous mixing. Then we sinter this mixture of the precursor raw materials at high temperatures so that this solid state reaction takes place that you see there. And if everything goes well, a single phase perovskite is formed according to the stoichiometry that we selected. If we click here, for instance, we see that here the problem is, the issue is to obtain single phase perovskites, but because of the high temperature, the powder that comes out is heavily sintered into single chunks sometimes, and this has to be milled first, let's say, to bigger pieces that can be handled, and then if we click by typical ceramic processing milling techniques, we can either dry or wet mill it in small lab quantities or in larger ball mill furnaces. And the idea of this milling step, if we click again, is to obtain a processable fine powder for the next shaping techniques. Which are these shaping techniques? We click and we see it, for instance, to make foams or extruded honeycombs. In the second case, we need to prepare a dough, a stiff dough that is extruded through a die, as we will show later. For the manufacture of foams, we make slurries and we coat polyurethane templates with the addition of organic binders and dispersant in both cases. We shape, let's say, the green body, we dry it, and the target of this step is, we click, is to obtain a rigid, handleable, green shaped porous structure. Finally, the last step is to sinter this shaped structure again at high temperatures, 1200 to 1350, in order to obtain robust, flow-free, and sintered porous structures with which we can assemble our unit. If we click, we will see which kind of structure we would like to obtain, and these are manufactures in the project, as I will show later. So here is the overall procedure, and now what are the properties of merit that we want to obtain out of this process? On the left-hand side, we have the powders. On the right-hand side, we have the porous structured body. As we said in the beginning, both have to be based on environmental friendly and health neutral elements. And then we start, let's say, with common logic, common sense. We need reasonable raw materials costs, scalable and energetically optimal synthesis route, and the same goes for the porous bodies. We need reasonable powder processing and shaping costs, and similarly scalable and optimal shaping routes. As we said before, we need our compositions to have thermal stability, to have a melting point above 1100, preferably up to 1300. And as we mentioned, we need phase purity, single phase, no secondary phases. And as we discussed about some systems, these systems have to be reduced at reasonable temperatures. And of course, we need to reproduce all these properties to the powder, from the powder to the porous body. The fundamental properties of merit, as it was stressed, is the heat of oxidation and the heat capacity. One is a measure of the sensible heat, the other of thermochemical. Together, they give us the hybrid sensible thermochemical storage capacity of the materials, which of course we want to maximize. And as we said before, we don't want these compositions to have any phase transformation in the range of interest. We don't want them, of course, because we cycle them from ambient to high temperatures, they will suffer some expansion and contraction, and not only thermal, but thermochemical, but we want this to be reversible and small if non-zero, and all these materials and shaped bodies to have thermomechanical and dimensional stability so that they don't crack or collapse under this cycling. Of course, as we said, we need both the green and the cinder bodies to be handleable, to have mechanical strength at satisfactory level, high permeability in order for the hot air, cold air to flow through them. And that's why we investigate other porous structures to enhance the heat transfer to the heat transfer fluid. So these are the criteria that we screen our materials as we go along this chain, this value chain process. And if we click, for instance, I will show some representative tests with respect to such properties that we use to screen our materials for. Okay, for instance, with respect, if you click 2 or 3 times, so the first criterion, which is the phase purity and energetic optimization, here we see the phase composition of a calcium doped, of a strontium doped calcium manganite perovskite as a function of how the sintering plateau temperature, you see it varies from 2 hours to 24 hours. And we see that for this composition in these conditions, the major phase is calcium manganite doped with strontium. All the projects are single phase with minute quantities of a secondary phase. And if we click, we can also see that by calculating once more please, the purity of the phase, we need that this is phase-wise almost pure perovskite, and we don't need very high sintering temperatures to achieve that, but this can be achieved only, let's say, even in the first 2 hours of sintering. Another criterion that we see in the next slide is the sensible heat contribution. As we said before, here we measure the CP of various composition as a function of temperature, the temperature that we are interested in, from ambient to 1200. And we see that the CP, if we can click once or twice more, what happens, the CP increases with temperature, okay? So, which is good because the sensible storage increases at the higher it is that we want. Some compositions are characterized by sharp peaks, which indicate that as we heat the material, a phase transformation happens, which might or might not be reversible, but even so, we don't want it because it leads possibly to detrimental expansion and contraction and affects structural integrity, and so such compositions are excluded. And of course, such graphs are a merit of materials versus each other. For instance, we can see that the olive composition there is better than, it has a higher CP, means that the green composition, and among the ones tested, the magenta one, let's say, shows the best performance, the highest CP, followed by the purple and the brown one. Okay, if we go to the next slide, we see some other screening. Here we see all these kind of structures that we synthesized, we shaped in this project as tailored, let's say, to the various diagnostic instruments. We shape very tiny mini foams and honeycombs on the top left that can go on a TGA. We shape 1 inch honeycombs and forms of different cross-section that you see that are good for diagnostic instruments and laboratory furnaces like the red ones you see there, and also mechanical tests as you see below, crushing strength tests. And we shape also larger dimensions of honeycombs and forms which are suited for temperature rings, testing temperature rings like the furnace you see on the right-hand side, which have a bigger diameter tube and can accommodate specimens of higher diameter as you see below for thermochemical tests. The next slide shows this kind of honeycombs that are produced in CERTH by extrusion, as you can see here, 2 different CPSI. CPSI is channels per square inch. It's essentially, as you can see in the photographs, how many channels available for gas flow has its porous structure there. And you see how these objects come out of an extruder, this stiff dough that comes out of the die that defines the channels, and then it's dried and then shaped and sintered to become a rigid cylinder, as you can see there. This kind of rigid specimens after the calcination, we go to the next slide and we see, for instance, tests with respect to their mechanical strength. We do crushing strength of this kind of materials, of this kind of specimens, and that we also can record, and we can identify where the material fractures, let's say, along the stress strain curve, as you can see there with successive photographs. Next slide shows quantitative results of such comparisons. If we click once or twice more, we see, for instance, our in-house synthesized honeycombs versus commercial cordialite ones. And what we can see here is that the in-house have much higher strength, which is primarily due to their thicker channels. They have lower number of channels per square inch than the commercial ones. As you can see there, the commercial ones have an order of magnitude more. And of course, this means that the solid surface that bears the load is higher in the case of our specimens, so that's why they have a higher mechanical strength. And if we click once or twice more, we can see also that the effect of composition and the walls have an effect. Structures of the same compositions but with thicker walls, less CPSI, they have a higher strength, as you see in the magenta curves, whereas proper dopant can improve further the mechanical strength for the same compositions, and that's how we get the green curve there. Next slide, please. This shows how we can assemble the big units either from honeycombs or from foams. So it's not necessary, and it's also very dangerous in case of cracks, to have a single monolithic body of the dimensions that we want. Industries that are doing this stuff, they produce so-called segmented pore structures. One can extrude or make out of foams smaller pieces that are easier to manufacture, and they also are replaceable, and this shows the concept of modularity. One can assemble units of bigger dimensions along and across from smaller elemental pieces that are easier to manufacture in defect-free cases. And if we go to the next slide, we will see actually how our partner LANDSON has scaled up these extrusion techniques. Here we see a perovskite body extruded in an extruder of diameter of 80 millimeters, 8 centimeters. You can see that it's practically flawless by naked eye, a perfect honeycomb, and a large one. And if we click to the next slide, we will see how one can build, let's say, extrude smaller pieces of hexagonal or square cross section with square channels or circular cross channels, circular cross section of the channels, and with this to assemble a bigger modular unit in 3 dimensions. And that's the end of the presentation. I think the next one is only the thank you slide, and this will, I guess, will be a good introduction for the next presentation that we will show the reactor made out of such components. Thank you very much.
Thank you, Christos. Yeah. So moving on to the next presentation, my colleague Leonidas Kastapidis will show us a few things about our testing of these materials in what we call the pre-pilot scale storage reactor. Leonidas, the floor.
Thank you, Nicholas. So we at CERTH are in charge mainly for testing the technology at small lab and larger pilot reactor scales. Next slide, please, Nicholas. So after validating the thermochemical behavior of our storage material at the lab scale, the next step was to test the process at the pre-pilot level under more realistic conditions. This scale-up phase is critical because it reveals new challenges related to geometry, heat transfer, material stability, factors that don't necessarily appear at a small scale. So we began by producing new extruded segments of the storage material, which required fine-tuning both the calcination parameters and the formulation for extrusion. This optimization allowed us to achieve mechanically stable and well-shaped pieces, capable of withstanding the repeated redox cycling at the high temperatures. So the final segments had a hexagonal cross-section with cylindrical flow-through channels to maximize contact surface area and enable efficient gas flow through during reduction and the oxidation phases. Next slide, please. So these segments were cut carefully and packed to form the honeycomb-like core of the reactor. The honeycomb geometry provides mechanical stability, but also ensures good gas permeability and efficient heat transfer between the solid material and the flowing gases. The pre-pilot reactor assembly consists of 4 layers of these hexagonal segment elements. The central channel houses the heating element, which provides the necessary energy input for the reduction phase. And around it, we placed a layer of insulation to prevent unwanted gas flow through the center and to reduce the radial heat losses. In total, 12 temperature measurements points were acquired from 6 thermocouples that were inserted axially and vertically through the structure. The configuration provides detailed picture of the internal temperature distribution, both during reduction and oxidation. And it also helps us identify any thermal gradients or uneven heating, which are key issues for scaling up the technology. Next slide, please. The complete redox assembly made from the CS10MO material weighs around 3 kilograms with an overall diameter of 130 millimeters and a height of 170 millimeters. The reactor was placed inside a metal canister, which is externally insulated and connected to the gas and power control systems. Next slide, please. During operation, we used nitrogen as the inner gas for the reduction phase and air for the oxidation phase. Both flows were regulated using a mass flow controller to precisely control the flow rates and the residence times. At the outlet, an oxygen sensor continuously monitored the redox reaction, allowing us to evaluate the conversion and the kinetics of the process. The electrical power input to the heating element was also monitored together with thermocouple readings to obtain a full energy and temperature profile of each cycle. So this comprehensive data set allows us to analyze the efficiency and the stability of the system under this cyclic operation. The next slide, please. So far the results are quite promising. We successfully validated the cyclic redox thermochemical process under the pre-pilot conditions, demonstrating that the material maintains its performance and structural integrity even at a larger scale. The heat effects achieved are more than 70% of those observed at small laboratory experiments, which shows that the process scales well with only moderate losses due to the thermal inefficiencies. In terms of energy performance, we achieved an energy density of up to approximately 600 watt hours per liter of storage material, which is a significant figure for the thermochemical system of this type. This confirms also the material's capability to store and release the heat effectively over the multiple redox cycles. Next slide, please. However, as with any scale-up step, several challenges have emerged. So the two main ones are the high heat losses and the special temperature inhomogeneity within the reactor. The heat losses are mostly associated with the external insulation and the relatively high surface to volume ratio of this pre-pilot system. Temperature inhomogeneity is partly due to the geometry and the position of the heating element, which can lead to uneven reduction and oxidation, especially near the outer regions of the material. Next slide, please. So to address these challenges, we already planning the next steps towards the pilot scale system. The main objectives are to improve the uniformity of the temperature field and to increase the effective heat transfer to and from the material. Specifically, the pilot design will include more heating elements per volume of storage material, likely 6 instead of 1, to distribute the heat more evenly across the reactor. We also plan to improve the radial insulation, which should significantly reduce the heat losses and help stabilize the temperature profile. Next slide, please. Another important modification will be to adjust the reactor geometry, making it longer and allowing for a reversible gas flow. This will increase the contact time between the reactive gas and the storage material and help us achieve a more uniform thermal distribution. The reverse flow capability is especially important for reducing the colder regions and improving the overall reduction degree of the material. Altogether, these improvements will guide us to from pre-pilot validation towards a fully optimized pilot scale reactor capable of demonstrating the technology under closer to industrial applications. This step will also provide us valuable data for process modeling, control, and potential scale-up to commercial applications. So in summary, the pre-pilot stage has been a key milestone in confirming both the feasibility and the scalability of the thermochemical storage process. We have proven that the material can operate reliably under realistic conditions and identified the key design parameters for the next phase. The lessons learned here will directly inform the pilot system design and move us one step closer to a practical and efficient and durable thermal energy storage technology. So thank you from me.
Thank you, Leonidas. So from the experimental work, we now go to more computationally oriented work. Our colleague Tian Chao from the University of Twente will present some results of simulating application scenarios based on this thermal storage concept.
Hello, I'm Tian Chao from Twente, and I'm going to introduce two industrial application scenarios for HERCULES. My presentation will go from the four aspects: motivation, Tata's use case, and Alucha's case, and the future work. Next. Yeah. Yeah, from the assessment result, the assessment of progress towards net zero emission by 2050, almost all the industrial sectors is not on track. So this means that industrial decarbonization has been very slow and present significant challenges. The challenge mainly comes from these three aspects. They are the renewable energy intermittency, and you know that in the many industry processes, they will cover a lot of high temperature processes and variable chemical reactions. This makes it difficult to be replaced by some new tech. So HERCULES was proposed to utilize the renewable energy and to provide clean heat to the traditional industrial processes. Okay, next. And the first scenario is based on Tata Steel's iron smelting process. So how does the existing process work? From the diagram, you can see that there will be 4 staffs to serve the hot air to the furnace. There will be 2 working status of the staff. They are on blast and on gas. You can think that they are discharging and the charging process of the storage system. In charging status of the staff, the combustion of furnace gas will heat the brakes in the stuff, and actually the brakes works as a kind of sensible heat storage. And in the discharging process, the brakes will heat the air flow in and then provide the hot air to the furnace. In the actual process, there will be 4 staffs to ensure the stable energy supply for the iron smelting, while in this diagram, we only show 2 of them to explain how it works. For Tata Steel, they need the hot air temperature over 1000 degrees C at this very high flow rate, and the heating power is around 100 megawatt. And in the existing and the system simulation we have done, we use 2 HERCULES reactors to fulfill the energy supply of Tata Steel. Next slide. There are 2 integration concepts for Tata Steel. The first one is very similar to the existing process. We just replace the stops using the HERCULES reactors. So we use the HERCULES reactors to meet all the energy demand of this process. In this case, the reactors will keep working. So this may increase the cycle number of the material and will lead to a frequent replacement. And next slide. And the second concept, we introduce one electric air heater as the primary heating method of the hot air. And the HERCULES reactor works as a real energy storage reactor to address the instability of renewable energy. But in this case, the problem is the performance of electric air heater is not that good under high temperature. The next one. And the reactor model we used in the system simulation in this stage is this one. Is the mass is around 110, and the volume is 82 cubic meters, and the capacity of energy is 61 megawatt hour. Next slide. We carried out the same research on both concept 1 and concept 2. Here we only show the result, part of the results from concept 1. After the optimization, we found that if we use 18 wind turbines and 110 for each module and 2 reactors, we will get the highest benefit and the cost ratio. And in this case, comparing with the existing process, we can reduce about 32% of the gas consumption. Yeah, we also analyzed the yearly and daily system dynamic response. Here we only use the daily response in 14th April, for example. We can see that the purple and the red curve are the temperature of reactor 1 and reactor 2. And it's obvious that when the temperature goes higher, it is charging process, and when the temperature decreases, it is discharging process. And the blue curve at the bottom, we can think it is a kind of the monitor of working status. When the blue curve is 0, it means that HERCULES system is providing the energy. When it is the 1, it means that the HERCULES cannot work at this stage, so we need some gas as the backup. This is the daily dynamic, and we can see that you only use 2 reactors. It's very hard to fulfill a totally stable energy supply for this case. So we may need more 3 or 4 reactors to fulfill a stable energy supply for industry. And the next slide. And the second scenario based on Alucha's paper sludge recycle process. We will focus on the red part, and the air will be heated. We use the natural gas, use the pyrolysis oil, and the processed gas. These 3 parts. And next slide. We'll focus on this area. The demand and the integration concept of Alucha's case will be here. We can see that Alucha's need around 700 degree air to under this kind of flow rate, and during the communication with Alucha, the HERCULES is hoped can replace the natural gas and pyrolysis oil, these 2 parts. So the heating power will be 655 kilowatt. Based on this kind of demand, we think the concept 1 is a feasible method to integrate HERCULES into Alucha's case. The same, we will consider to use 3 or 4 reactors in total, but here we only use 2 reactors to show the working status to meet Alucha's case, and consider the parameters of CS10MO and the existing system simulation from Tata Steel. We carry out a reasonable scale estimation, and the results show that we may need around 6.55 cubic meter or 13.8 tons of of the reactive material, and they will be filled in 3 or 4 reactors to fulfill the need of Alucha's case. The next slide. As for the future work, we have 2 scenarios for Tata Steel's case. In this stage, we use cobra oxide. In this stage simulation, we use cobra oxide as the storage material, and we only use 2 reactors to fulfill the energy supply. But we found we cannot fulfill it. So in the future work, the first thing is we will update the new kinetic model to use the CS10MO as a storage material. The second thing is we will simulate more reactors, 3 or 4 in more cases, and enrich the operation strategy to fulfill a stable energy supply. As for the Alucha's case, we just finished the definition of the system requirement. Based on the requirement and the similar research method or system of Tata case, in the future work, we will simulate the system model of Alucha case, and of course, to enrich the operation strategy and provide more selections. I think that's all from my part. Thank you.
Thank you, Tianchao. Okay, and I must apologize for our overrun, partly due to waiting for a few minutes at the beginning for people to join. We only have one more presentation before the question and answer session. And so now I give the floor to our colleagues from the Research Institutes of Sweden, Kristin Fransson and Yun Lim.
Yes, thank you, Nicholas. And we will talk about the life cycle assessment of one of the industrial cases that are assessed in HERCULES. And that's the Alucha case that Tianchao mentioned before. So next slide, please. And at Alucha, they have a process for upcycling of waste paper sludge to make it a new product that's a high-value circular calcium carbonate. And in that process, they use heat in several ways. And in the current design, the heat is they get the heat from combustion of natural gas, combustion of net process gas, and combustion of pyrolysis oil. But with HERCULES, they could instead use electricity that they can store in the HERCULES system for a large share of the heat supply. So they would reduce the combustion of natural gas, also reduce the combustion of pyrolysis oil, and instead sell that oil on the market. And they will get the possibility with the storage in HERCULES to use renewable energy that might not be available all over the day. So next slide. So here are the process chart from a life cycle perspective for the Alucha case for the current process. And we only focus on the heat demand for the process. Of course, the gray box is much more complex than what is shown in this figure. But HERCULES is of interest for the heat demand. So in the current situation, they use natural gas, pyrolysis oil, and process gas to get the flue gas that then is by different kinds of heat exchanges used in the CCC production process. And when we make the calculations for the LCA, we use the declared unit that is the heat demand to fulfill 1 hour of production of CCC. So that is what we calculate everything against in the LCA. So in next slide, we can instead see what it would look like if we use HERCULES instead for the heat demand. We still have some combustion of natural gas because that is needed to make the process run smooth. And we still have the combustion of the process gas that you get from the pyrolysis of the waste paper sludge. But you use less natural gas, and instead you use heat from electricity that has been stored in HERCULES. And you see down in the picture, there's this replaced production of oil. And that is what we in LCA language call a system expansion. So you get credits for not needing to produce that oil somewhere else. And also in this case, we use this declared unit of heat demand to fulfill 1 hour of CCC production. So the product, the CCC, it's the same in both systems. It's only the heating system that changes. So if we go to the next slide, we made some system design assumptions based on what Jan just said and also the other parts of the HERCULES project. So we use 4 HERCULES reactors to make it possible to store the energy and use renewable electricity. The active material is the CS10MO, and the total amount of active material is 6.5 cubic meters. We have made an assumption that the lifetime of the reactor is 5 years, which is quite conservative, we think. We think it will have a longer lifetime, but in this way we don't overestimate the benefits of HERCULES. And we base the reactor on the lab scale reactor because the pilot scale is not yet finalized. So it's a lab scale reactor, but we have upscaled it based on the outer area of it. And we assume that there are 10% heat losses in the system. And we also assume that there's a continuous production, so the system is running, the process is running day and night. So next slide, please. And there we have the input data for the LCA method. And as I said, the functional unit is 1 hour of production or 1 hour of heat demand for production of CCC. And for the system expansion, we assume that pyrolysis oil can replace the heavy fuel oil based on energy content. And we use software CMA Pro and the EcoInvent database for secondary data. And we have assessed several electricity mixes because we think that it's interesting which type of electricity that is used, and wanted to investigate how that affects the benefits of HERCULES. So we have assessed the market mix in the Netherlands in 2024, and also only the renewable share of the market mix in the Netherlands, and also wind power and the European production mix for the same year. And in the next slide, we can see in more detail the electricity mixes and what they consist of. And to the left, we have the Netherlands electricity mix, which consists of natural gas and wind are the main parts, and quite a lot of solar now as well. And this mix is constantly changing, so it's becoming more and more renewable for every year. And to the right, you see the European electricity mix, which has a lot more nuclear than the one in the Netherlands, and also more hydropower. And so it has less natural gas and also less wind power and less solar. And in the middle, it's only the breakdown of the renewable mix, which is the same as in the left diagram. And if you go on to the results, which is the next slide. Starting from the left, it's the current design. And you can see that it is mostly the production and combustion of natural gas that has a climate impact. And when you go to the next bar in the diagram, you see that when you use HERCULES with the market mix of electricity in the Netherlands, the yellow part of the bar becomes really large, meaning that the climate impact of the electricity needed to supply the heat for HERCULES has high climate impact. You also see that there's a negative bar, which is the replaced oil, that you don't need to produce oil somewhere else when you sell the pyrolysis oil. If you instead use the renewable market mix in the Netherlands or wind power, you see that the yellow bar gets smaller. You need less climate. You get less climate impact from the heat generation than when you use the market mix. And for both of them, you see that the black dot, which is the total climate impact of the heat delivered to the CCC production process per hour, is smaller than in the current design. So with the renewable mix, you get benefits of using HERCULES. But if you look to the right, you see that the yellow bar grows bigger again with the European production mix, and the black dot has a higher value than the current design. So if we go to the next slide, we have some conclusions. And the first is that the electricity for the heat generation, it has the high impact in most cases when using HERCULES. And it is very important which electricity mix you use when you assess the benefits or potential benefits of the HERCULES system. And for the current systems, it's the production and combustion of natural gas that is most important and has the highest impact. There is a benefit for HERCULES, but then you need to use it as the original thought is, to use renewable electricity for the heat generation, like wind or solar power. Then you can see that there are potential benefits of it. And I also want to say that these are preliminary assessments. We need more input from all the partners in the project when we have done more research in the project. But we think that this is an indication of how it will look like also later on. Yes, and I think that's all for the LCA. Thank you, Nicholas.
Thank you, Christine. So, thank you to everyone for your attendance. Thank you to our presenters for your kind preparation and presenting your results. This video from this workshop will be posted on our YouTube channel. And here you can also see some of our contact information to reach out to us if in the future you have some comment or question or wish to discuss any of the material we have shown. Okay.
Perfect. Thank you, Nicholas. Thank you, everyone.
Thank you, Nicholas.
All right.
Thank you, everyone.
Thank you.
Thank you.
Thank you,
Bye.
Nicholas.
Bye-bye, everybody.
Bye.
Bye.
Bye, everybody. Thank you.